Hi, so good afternoon. I'm Yoav Schechner from Technion. I chair the session. We're starting with an invited talk. We're glad to have here Alexandre Alahi from here is a local professor from EPFL. Prior to that, he was in Stanford University. His research is combining computer vision, machine learning, robotics, and transportation and mobility. He won several awards, and in particular, he actually won awards also on his entrepreneurial records. He founded several startups, and in particular, one of his research directions, which is about tracking of pedestrians in the public locations like train stations, is being commercialized as well. So it's going to be very interesting.
Thank you for the presentation. Welcome everyone in Lausanne. I hope you're having a good time and you have a great weather, so it's fantastic. And you will have a lot of fun tonight at the Olympic Museum. Today I want to talk about representation learning in general, and I will use my application of interest to demonstrate some of the ideas that I have to improve this field of representation learning. So let me introduce you right away to our robot, Lumo, navigating alongside pedestrian in Lausanne. This is in front of the train station. And the goal of our robot is to basically detect everything, understand everything around its surrounding, and plan a path according to what it has understood and detected. What the robot is using, representation learning. Usually we have a camera, an image, goes into a neural network. We learn a latent representation, and it outputs what we want. In this case, the pose. If you have been in the field for the past 15 years, this usually is the state of the art to do any detection or any perception task. What we are also doing in the lab, we try to use the same architecture, the same neural network to do multiple tasks jointly. And the idea is to learn a shared representation that can detect the human pose, the action, the focus of attention, anything related to understanding humans. Now, when you do that, you have to be careful about a lot of things. One of them is when you have all these tasks, how can you best deal with the gradient that comes from all these losses? Each of these tasks has a loss, and you need to be very careful to not have exploding gradient or vanishing gradient. And this is really the field of multitask learning. I think you already had the talk from Amir Zamir, who is also one of the leaders in this area. And here, what we in this paper, what we wanted to say is that if you're careful about the gradient for each of these tasks and you normalize it smartly, you can actually do up to any number of tasks you want without necessarily losing performance compared to using a single network doing the same task. So, for instance, we show that we can extract 32 attributes on humans given a single neural network and matching the performance of having independent network for each of these tasks. But by using one, it's much more efficient, memory and computational efficient. Now, so this is a representation learning in short. And to sum up, we can basically detect anything we want if we have enough data. This is the current state of the field. You can detect skeletons in any kind of condition, segment anything, and you can also generate almost anything you want as long as you have enough data. And yet, there are other applications that we're not yet able to succeed in using representation learning. So, and one of them is self-driving car. Let's look at the AI of a self-driving car. The first step is perception, computer vision. We want to detect everything. And then, usually the next step is plan a path accordingly. In this scenario, we are able to really detect everything at 100% accuracy it's all good. And then we can plan the path of this self-driving car. But something is missing. If you see the pedestrian on the right, can you predict what the pedestrian will do in the next 2-3 seconds? What he will do? Cross, right? So, but he's not supposed to cross, and he's static. But you're right. This is what happened. The pedestrian wanted to cross to catch the bus. So these two pillars that were quite popular in the field of autonomous driving and also within the industry are not good enough. So we need to bring another pillar, which I like to call it social forecasting, and which is in charge of predicting human behavior to then better do planning. But then when you want to also do better prediction of the world, you might want to rethink how you want to perceive the world, because right now, if we detect everything and we put a bounding box around pedestrian or this vehicle, it will still be very difficult to develop an algorithm that can take this as an input and do prediction. So we have to rethink, and what we believe we should, for instance, now extract more information on humans, such as eye contact, skeleton, body pose, the focus of attention, all these cues that we subconsciously use to communicate our intention. And this is what you guys used to predict that this pedestrian might cross the street. And if we go back to our robot will struggle to navigate this type of crowd. And similarly, if we look at other public robots in hotels, this was last month in Korea, I filmed it, it struggled to deal with humans exiting the elevator. And it was actually a mess, quite funny interactions. Even Honda is developing one, and this is after my visit in Japan, and it still struggled to follow me. It was supposed to follow me, but even this very simple environment, it was not that trivial. So if we look at its AI again, the first step is detect everything, detect humans. The second step was, I would say, planning. And I again argue that this is not good enough, because we need to predict that it's not okay to go between these two people talking to each other, and we should also predict that this person is walking. So these two paths, although they are physically possible, they are not socially accepted, so we should take only that path to control the navigation of the robot. So if you combine all these pillars, you have what we call socially aware AI. And over the past now 7 years in our lab, we tried to develop new algorithms for each of these pillars, shared new library for each of these pillars based on representation learning. So we did this. So we really look at all these tasks using representation learning. But after all these years, we noticed that we still are missing a lot of key elements. So the first thing is for perception, we are not able to detect rare actions, rare events. Because as I told you, we are able to detect as long as we have enough example of whatever we want to detect. In the context of self-driving car, there are a lot of rare interactions and action that even if you go collect data from the same city for a month, for a year, you might not observe, and they could happen in reality. And then for the prediction, we noticed that prediction was always addressed with knowledge-driven method. In the 90s, with like social force model, with maybe Kalman filter or extended Kalman filters to do prediction. And then in 2015, there was an era of deep learning methods to solve this prediction task. And we noticed and we proved that nowadays the deep learning methods to do prediction have not necessarily learned basic behaviors. And I'm going to share how we can address that. And finally, with respect to planning, I'm also going to talk more about that. We noticed that none of the existing methods are robust to distributional shift. So, having identified all these challenges, and these are the reasons that we don't see self-driving car nowadays, or any type of system that should interact with humans in the real world without making any mistakes, we proposed 7 principles to address these challenges. So let me go one by one. Actually, I'm going to start with the first 2 because they are quite linked to each other. So the first principle of prediction is about learning to predict sensory input to then learn to solve other tasks. So this idea goes back to 1860. It's not new. Neuroscientists argue that our brain actively makes prediction about the world based on experience. And this is right now also the state of the art of foundation models or generative pre-trained transformer. They are learning a representation to predict the next signal that they want to predict. In case of ChatGPT, is the next word to predict text, but you can apply it to any other signal or domain. And then, once you have learned to predict your signal, there is a second step, which is this fine-tuning step in ChatGPT, which is based on the principle of opposite. I claim that learning is successful by means of opposite, through the contrast of positive and negative examples. And as Rumi said, things are known by their opposite. So this is also quite old knowledge, light by way of darkness, and so on. So if you want to learn a representation, we can stage it in 2 steps. Let's first learn to predict anything. As long as we have any signal, it can be text, it can be image, videos, any signals that we want. And then let's learn specific things with few examples that we might have to learn these specific tasks. And we have seen that this is currently also the state of the art, and this paradigm seems to be quite powerful. So if we look at our perception task for self-driving car, for instance, or we can now, instead of trying to predict some semantics, some attributes, or some discrete values, we can try to predict the signal itself. First, we have unlimited amount of data. We can collect easily data, and then fine-tune it with our specific task we want. And hopefully, we might need much, much less data. And we can also do this for prediction. We have actually started to collect a lot of data on human trajectories or vehicle trajectories or any agent trajectories. And we want to learn to predict these trajectories, and we believe that then we can use the representation that we have learned to do other things, extract other semantic with very few examples. But to still address this issue of detecting rare action, we can take advantage of the principle of multimodality because we believe that we can interpret the world with multiple senses. And recently, we noticed that there is not necessarily too much difference between an expert in audio, in NLP, or in computer vision. Potentially, you can use exactly the same architecture, a transformer-based architecture. You can take any modality, learn a common representation, and take advantage of all these different modalities with the same unified framework. And again, I think in one of your previous talks, we talked about multimodality. And this will allow us to take advantage of these other modalities. For instance, we can take advantage of the web, of all the data that exists in natural language, and align it with images to potentially do zero-shot, a few-shot learning, and to potentially detect these rare events that someone has described on the web, but not necessarily labeled on an image. The next principle is the principle of residual learning. The current paradigm to learn to predict, at least in the transportation field, is let's learn to predict everything from scratch. Let's collect data on vehicle trajectories, on pedestrian trajectories, and let's learn a neural network that will learn to predict these behaviors. But I argued that when we want to learn to predict human behavior, we don't necessarily need to do it from scratch. There are a lot of things that we know that are based on the physics. There are a lot of things that we cannot do that we know. There's a lot of knowledge that exists. The same thing for self-driving car or for driving. When I'm trying to predict what a car will do, I don't need to necessarily learn the basic behaviors of the car will follow the road, will not jump, will not, I don't know. So there is a bit of physics behind it that I can take advantage. So let's potentially use the neural network to learn what we struggle to explain. For instance, the social norms. In this example, we can think that we have one model that is based on physics or knowledge that will suggest an output, and then we use data to just correct this output given some bound that we have control on to make our decision. And we can also do the same for self-driving car. We know that potentially there is an area that the car can go physically. Let's only learn to predict within this area where the car should go and not try to learn it from scratch. The next principle is the concept of compositionality and sparsity. I'll go fast on this one. Basically, the idea here is that the world that we see or any signal that we collect might look complex at first, but they can be explained with few simple atoms of a dictionary, and the challenge is to learn these few atoms. And this is quite known also in signal processing, all the compressed sensing, all the sparsity-driven methods to solve inverse problem are based on this principle. The next one is causality. We know that causation is not correlation. We know that we're learning correlation in this framework. But there is a new field called causal representation learning, where we're trying to learn causal representation. It's a huge field by itself, but we are also looking at how we can bring causal labels to improve the learning of these representation with some intervention or with some simulation where we know the real causality in simulation and can we transfer it to the real world. And the last principle, almost on time, is the principle of in vivo practice. And this is my preferred one. I also like the others. But when you develop systems that must interact with humans, you cannot suppose that you can freeze whatever you have and it will always work. So if I even have a model that can predict human dynamics as good as human might change in time. They will change maybe their behavior in 1 month, in 1 year. We already know that they change across space, across cities, across culture. So how can we potentially learn something and then update it on the fly without necessarily requiring to go and collect data and do everything from scratch? And this is also a field from machine learning called test time adaptation, test time training, which is, I believe, something that we should also apply to this type of application to make sure that they are doing what we expect them to do across cities and across the years. So all these principles, you can apply them to develop systems, and the systems that I like the most are related to transportation and mobility. It can be self-driving car, trucks, bus, trains, robots, ships, drones, or even scooters. But there's a third application, a last application I want to also share with you, which I'm quite excited about, is to help paralyzed humans walk again. And this is in collaboration with our colleagues from the CHUV, who put a chip on humans who are paralyzed, and they can send electrical stimulation to their muscles so that they are able to walk again. And our collaboration is about using socially aware AI to help them walk in a very natural way so that you will not notice that they are paralyzed. So the way we can do that is first, with our robot, we can detect the skeleton of the paralyzed patient. We can predict what should be the ideal walking behavior of that person, and then control the stimulation accordingly to match what we believe should be the ideal walking behavior. And we have started to do that. So this is our robot that sends signals to the patient, and then the patient can move. Right now, it's still in a robotic way because we just want to make sure that we can control the framework. But ideally, because we can see the impact of the stimulation on the robot, we can make this much smoother and potentially more natural. Voila. To sum up, we have a set of principles. If you believe that they are wrong, come to me. If you think I missed some principles, come to me. Then you can apply it for different pillars of intelligent systems. And we want to demonstrate them on a few of them where we believe they are quite challenging. And to finish my talk, I want to show you this last example. Suppose you have this autonomous vehicle. It detects the puddle here, but also the pedestrian. What should the autonomous vehicle do? Avoid, right? So we can actually code this, maybe a hard code, that whenever you see a puddle, we should just avoid it. But the reality is AI must read humans because sometimes the humans do want to be splashed. So we still need AI to understand human. Thank you. Any questions?
Plenty of time for questions.
Thanks for the talk. So in the first part of your presentation, you talk about different tasks. So does it mean now if we add another task, do we have to retrain this kind of architecture, or can we leverage existing knowledge and make use of it?
So this is, I hope, with foundation models. And this is also, I hope, with the first two principles, which is let's learn a network, a backbone that is maybe generic enough for many other tasks. And whenever we add a task, all we have to do is just maybe to learn the head layers that take advantage of the backbone. That we don't need to retrain the whole backbone in potentially other tasks. That's the hope. We are not yet there, but this is where we want to go.
Thanks.
Thank you. Parsa, I think. Yeah.
Okay. I think that if you want to use these models in some serious scenarios like cars and everything, we kind of have to make them explainable. So, when, for example, when an accident happens or there are some special scenarios, how can we make them? Is it considered in developing these models or no?
Thank you for the question. Some people nowadays are using this vision language model in this context to bring more explanation to the decision. For instance, they have been trained to not only tell you what should be the steering wheel, but also based on which reasoning, based on what? Because there is a traffic light, because there is a stop sign, and they have labeled data where there is basically a sentence or someone sharing their reasoning for all these driving behavior. To me, this is still not necessarily explainable AI. They just changed the output space to be more fine-grained. So this is interesting to to give a more fine-grained answer as opposed to just the steering wheel. But then there's this other area where it's more about understanding the neural network, the input, saliency, map, and so on. What are the feature attributes that are generating the output and things like that. So there are these two lines of research trying to bring more explainability or interpretability to what we do.
Thanks.
Yes.
I mean, this is more of a philosophical question, I guess, but an 18-year-old will learn how to drive within a span of 2 months, and drive, quite fine after that. Clearly, they have a lot of internal representations that have been built over decades without actually driving at all. And so, that seems like a big disconnect between how autonomous systems are being trained right now, and I'm curious as to, what do you think about this?
But then that's in line with my first two principles, right? The first principle is saying, regardless of your application, if you have sensor input like images, just learn to predict what's happening. And we can do this on all data that we have, egocentric camera, even cameras are not. And then, once we have learned this latent representation that can potentially predict, let's fine-tune it on a few tasks, hopefully with much less examples, so that we can match this behavior that we humans are able to do. That's exactly the philosophy that I have.
Okay, thank you.
Great talk. I think it was very informative for people who weren't already knowledgeable about representation learning. So I'm really curious about predicting these rare events and how I guess current research is going about doing that, and in that case, what is research in the field doing about priorities in terms of these rare events? Who are they prioritizing in terms of the outcomes?
Well, I think then you're talking about more ethical decisions, what's your priority about, I don't know, animal, humans, or something else? I didn't.
Yeah.
Okay, so then this is also another area that I'm also very excited about. Whenever you have to develop a real system interact with humans, and then you will deal with the ethics of the humans. And this is one of the most common questions that we have in self-driving car. What is a good ethic to implement, especially when you have to face multiple options? This is a very easy example. Maybe at one point you will the car will need to make a decision on turning to hit a tree, jaywalker, or animals, right? And what we're doing in the lab, and what's also known in the field, is there's not such a thing as a universal ethic. I can make a study here. Even in this example, people might disagree. It's very interesting. There's always some people who have their own way of thinking, and this is quite beautiful. This is our free will, and nowadays we have it when we drive, right? Everybody is welcome to make their own decision on what to prioritize. The only difference is that we don't have much time, so we usually react instinctively. But now that we have time to think, because we can implement it, can we think about what is the smartest decision if we have all these challenges? So I think this is a beautiful opportunity to then have a committee that can sit and think of the consequence of all these decisions and come up with a set of rules, ethical rules for different scenarios. So what we're doing as a research, we're saying that, okay, what if there's this committee or maybe a single person that is knowledgeable about the ethic? How can we learn the ethic of that person or that community to transfer to a system? And so the challenge is, what should we ask as a question? And how can we validate that we have covered all the use cases of the world? So there's this game that we do want to ask the minimum number of questions so that it's feasible. And we also want to make sure that we want to test it with as many examples that we think we're covering all the use cases. And there's this interesting research question of what are the right questions and how can we prove that we generalize.
Thank you.
One more question. So I have a question.
No? You have a question?
So for what you're describing is how machines would adapt to live in the world of humans. When I think about it, humans actually adapted a lot due to machines. Okay, so you can think, okay, there's a car. 150 years ago, there were no cars. So you can say, okay, they would introduce cars that would be polite to people and not, but eventually we are now respecting the space of the cars and we don't jump into the road more than, we're really afraid of them. So the machines have changed the behavior of humans. Also now people are walking with smartphones in the streets, and if you would try to get training data of people walking with smartphones in the streets 20 years ago, you wouldn't have any.
Exactly.
So there's a feedback mechanism here between the humans and the machines. All right. So are you ever even thinking about this? That it's not only a one-way interaction where the machines somehow need to learn how humans behave and whatever. That there might be some feedback. I don't know if it's even converging or if it's chaotic.
So this is exactly this principle, test time adaptation, which is the machine should adapt to new behavior or even to humans that try to adapt to you. So this is absolutely happening. Regardless of the machine, humans change their behavior. So let's have a mechanism that by observing the world, you can update your representation on the fly so that you are actually being able to deal with this new behavior, which is what we humans are able to do. So I'm able to potentially adapt myself to people that behave differently than I was expecting. Yeah. So let's develop the same mechanism for the machines. Let's not suppose that once we have learned something, there's nothing we have to do. Basically, this is what we're saying.
All right,
thank you.
Do you need the pointer?
Yeah, I can have it.
Okay, maybe you can. Okay, should be good.
Middle name is my Dengxin.
All right. So the next talk, as you can see, is test time training for hyperspectral image super resolution, and the talk will be given by Dengxin.
Yeah, thank you. So, yeah, very nice. Good afternoon, everyone. So my name is Dengxin. So I come from Huawei Zurich Research Center. So previously, I also worked at ETH and Max Planck Institute. Yeah, presenting a paper. This is a paper by doctoral students that when I worked at ETH, I co-supervised with Wang. So it's about test time training for hyperspectral imaging. So first of all, let's check what is, very quick recap about the hyperspectral image. So for RGB image, we all know it, basically 3 channels, this is very standard. So basically going through this white filter, red and green and blue. But for hyperspectral image, actually we can have a lot of fine-grained channels, these narrowband channels, which actually provide a lot more information, which enable us to do a lot more interesting tasks. For instance, could be medical application, or this, for instance, oxygen, level detection, remote sensoring, some material analysis, or maybe some cultural heritage protection, all kinds of very, detailed application. Also could be food quality control. So we already see a lot of potential there. This is all about the potential of hyperspectral camera. But what is the reason that we still don't see that it has been applied so large scale like RGB camera? So the challenge is very hard to actually obtain that high quality hyperspectral image at a good speed, at a fast speed. So typical challenges, you could do like push broom technique. So basically, this can give you high spatial resolution, high spectral resolution, but it's actually quite slow. So you have a lot of motion blur because it's actually take time to really change like from one basic frequency to another one. Or you have some other techniques, basically this tunable filters, but it also have the same issue. Actually, it takes time to actually go from one frame to next frame. You have to wait for quite a long time. So this actually create another same problem like motion blur. You cannot really capture like very fast moving object, which is a challenge. But the third type of technology we call like a snapshot. So basically you take still like similar to RGB camera, you take like really quite fast, like take a frame. But this normally like it's a lower resolution because you have to sacrifice something, right? So, and then you have the low spatial resolution. So this comes to be quite a trendy like a direction. Then a lot of people working here with like neural network to increase the resolution afterwards, right? So basically use the software capability to increase this. This is also the topic of this talk. So in this paper, we are not really designing a new like algorithm to new network architecture for hyperspectral image super resolution, but rather than we actually look into a different direction where we see, okay, you have trained a model there, like a lot of people have designed a model there which can do hyperspectral image super resolution, but then like when you actually apply to the test data, as we already see in the previous talk, like test data, the distribution can be different, there are a lot of difference. Can we also learn like during test time where you have a single test sample, right? So that is the idea. So why is this actually interesting for this application? Exactly because training data for hyperspectral super resolution, normally they are small size because capturing this good quality of data is hard, as I already said, so the camera is expensive and quite slow, and they don't generalize very well, and normally like because it's trained on a small data set then to different samples. So we propose this test time training, so really to learn to better adapt to the test samples. Let's look at the typical like network architecture. People usually just feed like all the channels. Like you could have tens of channels or hundreds of channels that fit into a network. Then they try to regress this high resolution, the output of all channels. This is the idea. Then there's a hope that we hope the network actually also learns the interaction between all these channels, like from one narrow channel, let's say from 400 nanometers to 405 nanometers, hope that this narrow band, they interact with each other and then help each other, right? That is a hope. We will see this is not very easy to learn. And then there are also recent methods which actually decouple this in two stages. So first stage, we learn just a single channel, like just to increase the spatial resolution. Then we have a second stage. Basically, once you process every channel like separately, then you concatenate the result. Then you actually go through a network just to learn the kind of spectral refinement, let all the channels somehow talk to each other to improve the results jointly, right? But we find actually it's not necessary. So you just need to focus on this part, just to process single channel, do them properly, then you get almost the best result than any of this method. So I think there are two reasons of this. Like intuitively, as I said, let all the channels interact with each other. This is a very nice thing, right? Very natural. Like that's actually what the whole community was doing for quite some years. But the problem is that you have a lot of channels. Their difference is very subtle. Like if you just like through all the information together, that help the network to actually figure out, okay, how this subtle change to help each other is very complicated. So rather that the other channel information might actually introduce, like, let's say, pollute the head. I mean, instead of providing the right, like, helpful information, but it actually can also pollute the information of each of a single channel, right? So if you only focus on single channel resolution, then the network task is so much simpler. You can do a lot of good things. On top of that, you can also supervise this network with a much larger scale RGB training data set, right? Because you are not like learning the interaction between all the channels, but rather than just have a spatial super resolution network. That's why we actually choose to use this simple network, which already gives you the better performance, but it's also easier for test time adaptation, test time training, because there you only have a single training sample. You do need to have something very simple, very robust to use, right? Okay, so our idea is very simple. So this method is embarrassingly simple, but it works very, very in practice. So typical test time training is that you have input, then you give to a network, then you have this output, then you can treat this as kind of a pseudo label if you believe that the quality is good, right? Then you actually have a new training, like one training sample input, output, then you give to the network, then you refine your network, right? Or retune your network. But it doesn't work here because that is actually because it's a regression task. If you give this to the network again, just there's no gradient can be computed. So we do a very simple trick. So because here you have the input, real test time sample, you have the output. Then this output you can downsample it, right? Because you can downsample, create a new low resolution input, which will be very similar to this one. But this the good thing is that this pair, when you put together their low resolution and high resolution, they follow like the exact because this is downsampled from this one. So their low resolution, high resolution relationship is actually correct, right? So we actually use this to train your network, which actually worked very well. And on top of that, we add a few methods to increase the robustness. As I said, the training sample, you only have one training sample. It's very easy to the network is very easy to diverge. So basically, you drift away. So what we did is we also embed this teacher-students network into the training. So you train a student network, but you keep accumulating the weights. So you actually have something more robust. It's a network where you actually see over time a lot of training samples. I mean, of course, it's the same training sample, but you see a lot of different input output, this variation. So you accumulate a lot of knowledge. So we embed this into a network. So now this becomes 4 steps. So you downsample it, you train your students' networks, then you actually accumulate the weights. Basically, this is a teacher network which will be more robust, which is the accumulation of this students' networks knowledge over time. So then, I mean, you still have a problem here. This is still basically from one training sample, right? We are thinking, okay, can we actually increase the robustness more by actually augmenting the data? So because here you only have one training sample. Again, all these tricks is to increase the robustness so that you can really learn from one training sample without drifting away or overfitting to it, right? So there are, of course, I'm sure that everyone knows there are a lot of data augmentation techniques there. But most of them are designed for object detection, image classification, etc. But for low-level tasks, especially for image super resolution or hyperspectral image super resolution, there are not much there. So if you think about this typical data augmentation, they will break out the structure or the texture of the data, right? So it's not really suitable. So instead, we propose we call a spectral mix-up. Basically, just mix different channels. Let's say you have channel, first channel, second channel, third channel. So you can bring a bit of knowledge, you basically linearly blend multiple channels so that you actually synthesize a new channel which looks similar to the original input. That was this will be the whole algorithm. You downsample, create a new synthetic example, then you train basically your students' network, then you update the whole model. Here, of course, you augment the data, right? That's the whole method. Then for the dataset part, we use existing dataset, but we also collect our own dataset because we find existing dataset normally, I mean, it has been already there for quite many years. The richness is a bit lacking there, so we basically collect this data for different fruits, meat, different materials, try to increase the diversity. And here is the evaluation. So basically, we can see, okay, our method, I mean, all the components I introduced, pseudo labels, the students, teachers, mix up, all actually helped quite a lot. Overall, we see over 2 dB improvement over the original model. And then we see our test time training method improve the performance of this hyperspectral super resolution quite significantly. Also outperform other test time adaptation or learning method quite a lot. And then we ablation study for spectral mix-up compared to other augmentation method, we find a good improvement. And also we test our method with different network architecture that it improves over different architecture. some more results. You can also find this in the paper. That, for instance, the source model, our model. I mean, through the beamer, maybe you don't see them very well. Okay, then I just conclude in this slide. So very simple yet effective method for test time training for hyperspectral image super resolution. It outperformed other test time training method. It can be used as a plug-in method very easily to any super resolution method. So these are the three methods: just learn single channel and create good synthetic samples, and also increase robustness with a teacher-student framework and some good suitable data augmentation method. Yeah, thank you very much for your attention.
So you start with a low resolution HSI cube, upsample it, and then downsample it, and it seems like you assume that the result of that is different than the original input image. So doesn't that mean that the super resolution was in a sense wrong, or what's the relationship expected to be between the original low resolution HSI cube and the one that you get by super resolving and then downsampling?
Okay, so basically this synthetic sample, if I come back here, so basically you are saying that what is this relationship? I mean, here you can imagine this one is already very similar to this one, right? So your original model kind of works well. I mean, it's not perfect, but it's reasonable, right? Then if you downsample, then you create this pair. So this one is already similar to this one, but this one should be a perfect ground truth to this one, meaning that your network is will be further fine-tuned with a sample which is very similar to your actual input data, right? So if you fine-tune this with something very similar, then it should improve the performance for that exact sample, right? That's the idea.
Okay, but there's no sort of quantifiable relationship between the sample that you started with and the sample.
No, there's no. We actually tried. We actually tried to also blend these two or somehow to define. Okay, I mean, try to measure also the similarity between this one and this one to select somehow the more confident pixels, so that we only fine tune with this pixel and their prediction. And I mean, we haven't found obvious improvement there, so we keep it as simple as this. But of course, I mean, you can find some ways, as I said, like to measure the confidence or to know whether this, because this is the output. If you downsample, if you kind compare to this, and somehow you can get a sense of correctness, right? Whether it's correct or not. So you can use this to further improve the method. I think that is an interesting direction. We just simply tried and haven't go too deep there in that direction. Yeah, thank you.
There might be more questions. I have a question, but we don't have time.
Yeah, thank you.
Next speaker. Thank you.
Sorry about that. So, thank you so much. Okay.
All right, now we have a very interesting talk by Michael Zeeuw, Zeeuw, and Aswin. And Michael will be giving the talk about iridescence. Go ahead.
Thank you. Yeah, I'll be presenting our work on scanning iridescent reflectance. And so what kind of materials am I talking about here? So we're looking at materials like this that are exhibiting these very bright colors when we're observing it from this one particular direction. But we notice that if we change our viewpoint even just slightly, we notice that the appearance of these materials completely shifts. So we can see these color changes. We see the hologram in the bottom left is completely appeared in bright color. And so we're noticing that when we're trying to characterize and capture these types of materials, we're going to have to deal with very high frequency changes over just very small changes in observation or illumination angle. But we also notice that if we take one of these iridescent materials and rotate it around, or rotate our camera around it, these types of high frequency reflectance effects are also apparent over the entire hemisphere of reflectance. And so we're not only dealing with high frequency and high resolution needs, we also need to be able to measure and represent this over a very broad angular range. So this is a difficulty in terms of the amount of data that we need to capture, how efficiently we can represent it, and things of that nature. And so in this work, we represent both the data capture itself using a wide baseline light field camera, as well as a neural architecture to better represent this type of data using a data-driven reflectance model. So to start off with our imaging system, we apply this base design for a wide baseline light field camera that we introduced at ICCP 2 years ago. And what this does is it uses an ellipsoidal mirror to map a broad angular range of the light field that's propagating from the scene at one focal point to a far more measurable light field at the other focal point. And if we place a light field camera there using a microlens array placed in front of a sensor, we can capture very rich spatial and angular information in just a single image exposure. So we can see, for an example of the type of data capture that we have, under each of our microlenses that we have, we're capturing a very rich array of all of these different iridescent effects. And so the different spatial angular measurements that we have are really giving us a very rich data set in just a single image exposure. But there's a couple limitations if we just took this prior design and applied it directly to reflectance. One is being that we have a missing central cone. So this ellipsoidal mirror is mapping these broad angles, but it's not mapping any of the light rays along the optical axis. And this is a problem if we're trying to reconstruct the entire hemisphere of reflectance that's leaving these types of materials. Additionally, we have no illumination control. So if we're trying to reconstruct, say, across all 6 dimensions of a spatially varying VRDF, we need both spatial measurements, angular measurements and observation, but also different illumination conditions if we want to fully reconstruct these types of materials. So to start off with, consider how to resolve the missing central cone. We note that if we're observing our optical design, we actually have kind of an open gap here just above our sample where we have no measured light rays that are actually passing through. In addition, if we consider the measurement space, under each microlens, we actually have a missing gap of empty pixels that are present in the center that are also aligned with the optical axis. So we can use this to carefully design and place a lens within this gap to then map part of this central cone into this region of missing pixels. So we're both using the data that we have on our sensor more effectively by applying more pixels, but also we're filling in this missing portion of data that we had in our data system. And you can refer to our paper for more details of like how we place and design this lens position. But by doing so, we can kind of match the spatial and angular range that we had from our ellipsoidal mirror. So you can see how we implement this in the lab. So we modified a Nikon Z6 camera to produce a light field camera by placing the microlens in front of the sensor. We have our ellipsoidal mirror and our object placed at the lower focal point. And you can see on the right the lens placement. So we actually chose a Fresnel lens, which is like not ideal optics, but because of the light field camera that we have, we care less about some of the blurring and aberrations that we have. We're able to resolve some of those. But it allows us to reduce the occlusion that we have, since we can't just float a lens in free space. And so we chose the Fresnel lens to be limited occlusion in terms of mounting and its thickness itself. But you can notice also here at the bottom that we say we have calibrated illumination down here. So if we zoom in just above our object, we can see that we have right here on the left side this arc of LEDs that we place within the mirror system right above the object. And so this is because we need that dense illumination control. We're not able to just add illumination outside of the mirror. We need to cover all of these different angles. And so again, we sacrifice some occlusion, so we're losing some of our measurements by placing this blocking part of the mirror. But if we place this ring of LEDs or this arc of LEDs on a rotation stage, we're able to get fully continuous measurements in azimuth and then this discrete set of measurements in elevation to really give us very, very dense illumination control at the cost of just some of our light field measurements. And so with this, we're able to efficiently measure both space and observation angle in a single exposure and then add additional exposures to give us really this dense illumination measurements. But now that we have that, we've started adding a lot more data. And so just if we want a data-driven reflectance model, we can't just work directly from our data. We have way too much of it to do that efficiently. And so we developed this a neural representation of our SVBRDF because we have one image per illuminant. We have our calibrated light rays. We have calibrated illumination. So we can just treat this network as just basically a rendering network. So we can pass it a location, a observation direction, illumination direction, and it can render out the predicted color. The overall architecture is pretty simple. But one main thing that we found that was very important is the addition of siren activation functions in between. So we have this very, very high frequency data that's typically not seen. You typically would like to have some color consistency or something like that to really be able to train well on these types of learning the reflectance on these. So we add the siren activation, which is a sinusoidal feature vector essentially activating between each of these layers to allow us to represent these higher frequency angular effects in particular. We also, on our input, we still use a positional encoding, very similar to common approaches in NERF or IDR, things of that nature, to use Fourier features for spatial frequencies, but these angular effects we found were best implemented using the siren activation. We also have just a reparameterization block just to help center our angles within the surface normal of our material that we're trying to measure. And so with this representation that can output a predicted color, we can take this very rich data that we have, train a much simpler representation than all of this data that we've captured, and now we can produce these reconstructions of these very interesting iridescent effects. So we can note for this hologram, which is a common security feature on credit cards, that we're capturing all of these very rich angular effects in particular. So you notice as we spin this around, we're getting these very bright iridescent effects. In addition, for these other types of materials, note in this case that the viewpoint and illumination are not directly aligned, so they're not meant to be a one-to-one comparison here, but we're capturing these same effects in this case. We also are reconstructing these spatially varying reflectant materials, even iridescence that comes from alternate methods. So we have here a peacock feather that has a kind of a different way of producing its iridescence and capture some of those kinds of effects. And we don't have to do just novel viewpoint. We can do novel illumination synthesis by sweeping the light source back and forth. So we can see in the hologram that the bird seems to kind of shift back and forth, and that's kind of the 3D effect that's meant to be produced by that hologram. In addition, we can visualize the actual BRDFs that we are trying to reconstruct. So by fixing the spatial location, we can then visualize all of the different observation angles of that point for varying illumination conditions. And so we can see here that our model is very expressive. We're able to kind of handle these different types of iridescence where we have maybe the top one has all of these different iridescent spotlights that appear at a large variety of angles, versus some maybe have fewer but with different structure. The peacock feather kind of acts in its own different way that's slightly more diffuse. So we have lots of different types of iridescence that are all being able to be trained using just this same network architecture. In addition, because we have these SVBRDF representation, we could just transfer them as a texture map, essentially, a very rich reflectance texture map. And so we can transfer our iridescent reflectance that we've learned onto other geometries like what we've shown here. Finally, we can consider kind of the effect of all of our different design decisions that we've had along the way. So if we show kind of compared to our full result at the top, our Fresnel lens is very important in terms of filling in that central cone. So especially since we're trying to model very, very high frequencies, if we have a large missing section, it's just going to count that as essentially a blank section. So you essentially see on the far right for the skull, if you're looking straight at it, all of the normals facing you will just appear blank, but it will reconstruct the reflectance around the outsides. If we remove our siren activation and just do the positional encoding, we lose all the ability to do all these very, very rich angular features that we see. But if we remove the positional encoding and just rely on the siren activation, we're not able to reconstruct the spatial textures in the same way that we do with the positional encoding. And finally, if we just consider doing a Fourier feature encoding directly on the angular measurements as they input the network, that also doesn't capture the highest frequency features that we see that we can only capture with both the positional encoding and the siren activation in the network. Finally, we can validate to make sure that we're not just hallucinating some very interesting iridescent effects that look nice but aren't actually present in the data. And so if we note our data, say we train over a typical set, very dense illumination of 198 images, but we leave one of them out for validation, we see that we can very well reconstruct the original data as shown here on the bottom. So we're reconstructing all those same types of iridescent highlights. They were all present in the data, and we were able to reconstruct them with quality, PSNR, and structural similarity. And we can find that even as we reduce the number of images, so have sparser illumination control, and still leave one of the images out, we're able to reconstruct most of these effects. So our network really is very expressive at being able to reconstruct even this very complicated iridescent materials. And we can push this all the way to the failure case here with only 9 images, and then we won't be able to reconstruct that anymore. So in conclusion, we've shown the ability to both capture the very rich information in these iridescent reflectant objects, ability to also efficiently represent it using a neural architecture, and then the ability to reconstruct all these very interesting, complex reflectance effects. Thank you.
Very nice work, interesting. Given the high frequency, very high frequency content of the BRDF, how do you, or how does one distinguish spatial variations in the BRDF from minute variations in the surface normal?
Yeah, that's an excellent question, and is definitely was a significant challenge in the representation in particular. We definitely found that using the positional encoding with the siren activation allowed it to kind of learn both of those. One thing that we had to do is constrain our objects to planar materials so that we can be very sure of the spatial locations that we're observing. We've tried and wanted to do this in the past with like actually, just fully learning a representation of both the geometry and the reflectance, but then you just have no color consistency between different views and things like that. So just really careful calibration to make sure that we know, okay, this spatial location has these observations that we could train to be the reflectance of that point rather than textural things. So it's really constraining the geometry and careful calibration that lets us kind of trust that a single point is observing this color variation.
So my question was, does the angular resolution depend on the size of your mirror? And what prevents you from just having a larger mirror?
Yeah, that's a great question. Yeah, the design of the mirror itself does have a big impact on resolution, and we've done a lot of analysis of this in other works, just because it's also non-uniform because of the way the mapping works with the ellipsoidal mirror. So it's definitely a very complicated question to consider what does resolution mean for this kind of wide baseline camera that we've explored a lot. But the main question for like size is actually just the size of the objects that we can measure. So ideally, the bigger the mirror you have, the bigger the objects you can measure. But then it's just a practicality concern of how big of a mirror can you actually manufacture effectively. We've already had enough difficulties, a mirror of this size having the optical quality not be imaging quality necessarily, so that produces a lot of challenges for calibration in that sense. So just kind of a trade-off more in the engineering realm rather than practical limitations of like the theory of an ellipsoidal mirror. Yeah.
Okay, I have one more question. You can set up in the meanwhile. The angular resolution fundamentally is limited by the spectral resolution of your camera, because different wavelengths diffract in different angles, and eventually you integrate it with your Nikon camera. So that's essentially determines how well you can resolve features angularly with this effect. So are you taking this into account when you're designing your your representation by saying, okay, my camera has this and that bandwidth per spectral band, therefore I would expect that I will not be able to resolve angular effects, diffractive effects better than something, and therefore that may dictate how I should represent my angular samples in the network. Are you taking this into account?
That's a good question. I'd say in practice, especially in the lab prototype, we don't approach those limits as much as we approach other limits induced by pixel pitch or lenslet spacing and size and stuff like that. Mainly because of like some of the optical limitations with the quality of the mirror and the quality of like the Fresnel lens and something like that. We don't usually push against those theoretical limits as much, but that would be an interesting avenue to pursue, especially in simulation for like if you can get the optical quality better, are there limitations that come in due to those spectral qualities? Yeah.
Right,
all right, thank you.
Nice to meet you. Hi. So actually, I'm pretty interested with this talk because I've been talking to him through Zoom for a while, and then now it's the first time to meet him. How do you pronounce your name? Sorry. Juhyeon. All right. So he's going to talk about efficient time sampling strategy for transient absorption spectroscopy. Go ahead.
Thank you for introduction. Hi.
Today, I will present our work titled Efficient Time Sampling Strategy for Transient Absorption Spectroscopy. So, we all know chemical reactions. Mixing multiple reactant chemicals under certain conditions or shooting a laser to photoreactant chemical forms a new set of chemicals. But how fast is the reaction? Also, how are their physical structures of chemicals changing during the reaction? Chemical kinetics is a field of physical chemistry that studies such complex dynamics of chemical reactions. Centered to that field is time-resolved spectroscopy, which studies fast dynamic processes through spectroscopic techniques. With the help of pulsed laser, it is now possible to study various chemical reactions that occurs on timescales as short as nanoseconds up to femtoseconds. And these studies found applications including protein folding, useful for treat cancer, atomic vibration or electron dynamics to build better quantum computers, and surface catalysis to build better catalysts. In the last decade, the ICCP community has advanced a specific time-resolved spectroscopy known as Fluorescence Lifetime Imaging. But not all molecules are fluorescent. In that case, we can use different time-resolved spectroscopy known as Transient Absorption Spectroscopy. A brief introduction to how TAS works. The sample we are studying is in a cell called sample cell. TAS shoots two types of laser pulses to this sample cell. The first one is a pump pulse that excites the chemicals. The second one is a probe pulse, which is shot after a specific time delay t. If all chemicals are excited by the pump pulse, the probe pulse is not absorbed much by the sample. However, if chemicals relax to the ground state, the probe pulse is absorbed a lot. So we will track the probe pulse's absorption as a function of this time t. Not just that, using a diffraction grating and detector array, we can measure the probe pulse's absorption as a function of wavelengths. More details. We first measure the background absorption due to the probe pulse itself without pump pulse. In this case, the probe pulse excites several electrons from ground state G to excited state E, which results in absorption over wavelengths to have a specific peak at certain wavelengths. Next, we also shoot pump pulse, which is at high power, and hence, most electrons in ground state excite to E state, which depletes electrons in ground state, and we call this ground state bleaching. After time t, some excited electrons go back to the ground state. We then shoot the probe pulse for absorption measurement. Just like before, it excites electrons from G to E. But this time, we observe much lower peak due to ground state bleaching from pump pulse. However, at the same time, we can observe another peak due to electrons that jumps to even higher energy state E star. So we have two measurements, with and without pump pulses. By subtracting these two measurements, we get differential absorption, delta A. As explained before, we get two peaks with different signs due to ground state bleaching and absorption of excited states. Since we measure probe pulse multiple times over time t, we get different measured value over time as electrons go back to ground state. Theoretically, such decay could be modeled using exponential decay. Mathematically, delta A could be modeled as following expression.
Here, we are interested in decay rate tau, which is also known as lifetime, similar to film, but there is no fluorescence here. Tau can provide us information about molecular structure, reaction speed, protein unfolding rate. So chemistry researchers are very interested in accurately measuring lifetime tau. However, what we actually measure is these noisy samples. So, how can you obtain reliable lifetime from these noisy measurements? We do not want to use more samples as it already takes time in the order of hours to even days or weeks based on the study. Instead, in this project, we propose to use better sampling strategy that result in 5-time reduction in experiments. So, how do we do better sampling? Again, our goal is to minimize error of estimated lifetime compared to some ground truth value. We use nonlinear curve fitting algorithm like Gauss-Newton method to estimate tau. Unfortunately, directly solving this problem is not that applicable due to nonlinearity of curve fitting process. Instead, we can approximately achieve this by minimizing fluctuation by a new additional noisy sample. So here is our incremental approach. Assume that we already have parametric model for given noisy blue samples from curve fitting algorithm. This gives optimal parameter tau hat that minimizes error for each samples. And let's consider that we have new sample at t0, which is denoted as red point. This new sample will update the estimation on tau hat, which makes the fluctuation of delta. Considering the Gauss-Newton algorithm, the update state is inverse proportional to derivative with regards to parameter. Therefore, we want to find t0 that minimizes delta or maximizes the derivative. For exponential model, we can easily calculate this, and the optimal t0 is given at the point exactly same with tau. Also, we found that instead of full curve fitting algorithm, certain normalization process enhances the robustness of the proposed algorithm. Here we summarize our method. First, we sample at t equals 0 and get accurate value for a plus b. Also, we sample at t equals infinity and get accurate value for b. Then we sample focusing at t equals tau that maximizes partial derivative. Finally, we process data normalization and perform nonlinear curve fitting algorithm. We first verify our algorithm using simulation. We compared 4 different sampling strategies using uniform time sampling, exponential time sampling, derivative sampling that samples proportional to derivative value, and our proposed method. We also compared 3 different normalization strategies that use different amount of normalization. Here we assured every method to use same number of samples, including the samples used for normalization. For measurement noise, we used Gaussian noise profile estimated from real TAS measurements. Through several simulations under various conditions, we found that our method gives the best result. Especially, our method needs 5.5 times less samples compared to the widely used baseline to achieve the same amount of error. One caveat of our method is that we need some initial guess on the lifetime that is used for sampling. However, fortunately, we found that rough estimate with plus minus 50% of error is enough to guarantee the optimal performance of the proposed method. We also found that our method is robust under various noise profile and also superior to linear regression that applies logarithm to exponential data. We also conduct real TAS measurement for chemical curve for CZIPN. This figure is 2D absorption plot for time and wavelengths. Focusing on certain time range, we can find that exponential decay really occurs. To demonstrate effectiveness of our method, we compared our method to exponential sampling method, which is widely used in previous TAS works. We repeated the experiment 10 times and could find that our proposed method gives 6 times less standard deviation compared to the existing strategy in TAS works. In conclusion, in this work, we propose an efficient sampling algorithm that is applicable for TAS measurement. Using our method, we need 5.5 times less samples, which makes an hour experiment to only 10-minute length. We expect that our algorithm is not only useful for chemistry researchers, but also anyone who requires lifetime analysis. Thank you for listening.
Given that you want robustness, have you considered using robust estimation for computing, for doing the line fitting? So rather than using least squares, you just use a robust functional, and then the derivatives that you mentioned, this is just the influence function of your measure, I think.
Yeah, so it is true. So basically, there can be a lot of methods that is used for curve fitting algorithm, but in this work, we used Gauss-Newton method, one of the widely used curve fitting algorithm in practice. And so we measured the robustness of curve fitting algorithm using the variance. So it depends on the input data. It gives noisy data, noisy output, noisy estimation, and we estimate the variance of that output. So we measured the robustness, but yeah, that is how we implemented our algorithm.
So when you make measurements here, okay. So when you make when you apply this algorithm, the sampling strategy depends upon knowing an initial estimate for tau. And you were saying that it's kind of robust to errors in this initial estimate of tau. So I have two questions that are related to that. First, what if is it not common for their samples to have mixed samples? Meaning, is it not common to have two different samples that have two different tau mixed in? Is that not a case, and how would that affect the estimation strategy? And the second question is, when you do know that your tau estimate may not be accurate, does it make sense to think about how to reallocate those samples based on the variance in tau that you expect?
Okay, so for first questions, yeah, it is true. There can be several mixed chemicals with different lifetimes. That is true. But in many cases, they have really different scales. So one is in like femtosecond, one is in like nanosecond or millisecond. So we can safely ignore that term. So actually, that is why we have additional constant term B here. So to be accurate, that B is also exponential, but it has different time scales. So we approximated it as a constant term. But yeah, that could be further studied in future works. And so could you repeat the second question? I can.
If you know variance on estimate of tau that you're using, then is that something that you can use within your sampling strategy?
Variance of the tau. So I haven't thought that could be used for sampling, but yeah, actually that is used for the evaluation, variance of tau. Yeah, we only use that for evaluation, but yeah, it could be used for new sampling technique, but we haven't considered it.
Thank you.
All right, so the last talk of this session before we have the poster spotlights is end-to-end fluorescence lifetime imaging and optimized encoding and exposure allocation. It is somewhat related to the previous talk because it also talks about lifetime of the states. And the speaker will be Ziyi Guo.
We present end-to-end fluorescence lifetime imaging with optimized encoding and exposure allocation. First, we will explain the fluorescence lifetime. Fluorescence is a photoluminescence phenomenon. When we use a short light pulse to illuminate fluorescent material, the intensity of the emission light decays exponentially over time. When the intensity decays to 1e over the maximum, we refer the time to fluorescence lifetime. Because the fluorescence lifetime is related to fluorescent molecules as well as a microenvironment like temperature, pH, and so on. So it can provide important information which are not available in the fluorescence intensity measurement. So by utilizing fluorescence lifetime imaging microscopy or FLIM, we can perform early cancer detection, cellular metabolism monitoring, oxygen concentration measurement, and facilitate research in nanomaterials. Regarding the measurement of fluorescent lifetime, there are two dominant methods. One is time domain FLIM. It uses a short pulse of light for excitation and then records the exponential decay of fluorescent molecules directly. This approach provides high temporal resolution, but is slow because it can only be imaged by scanning and is complicated to process data. And high precision instruments are usually more expensive. Another is frequency domain FLIM. It uses a continuous excitation light with amplitude modulation over time, like a sine wave. The emission light shifts in phase and amplitude and can be demodulated in the frequency domain to get the fluorescence lifetime. Although it has faster acquisition speed, its signal-to-noise ratio is a serious problem. Over the years, more and more works try to improve the performance of FLIM from different perspectives. For example, one focuses on how to improve FLIM data processing, and there are several works that combine FLIM with deep learning by utilizing the powerful data processing capabilities of deep learning. They simplify the process of analyzing time domain FLIM data. The other is more concerned about how to efficiently collect FLIM data. Some works give new performance evaluation scheme and optimize a high performance coding scheme in frequency domain FLIM. However, these works still have some problems, such as the acquisition speed of time domain FLIM system is still slow and it needs expensive equipment. For frequency domain FLIM, exciting coding schemes are very limited for imaging in low signal-to-noise ratio environments. To overcome these problems based on the imaging system as shown, we model it as a differential forward model and combine it with a reconstruction network. We build an end-to-end flame system by calculating the loss function and using backpropagation. We can train and optimize the entire system to achieve high performance flame. The whole framework achieves the joint optimization of the coding functions, the allocation of exposure time, and the reconstruction network. Here, we introduce the differential forward model. Firstly, according to the real fluorescence lifetime and the fluorescence intensity, we can calculate the emission signal. In order to optimize the coding scheme for different scenarios and noise, we design the demodulation function to be composed of number parameters. At the same time, considering that different coding schemes has different signal-to-noise ratio, we introduce the optimization of the exposure time allocation. After adding noise, we can get the actual multi-measurements. So it's our differential forward model. To reconstruct the fluorescence lifetime from the multi-measurements, we propose a transformer-based fluorescence lifetime reconstruction network. The overall architecture of the network is implemented based on a U-shaped transformer-based encoder-decoder framework comprising of channel feature extraction and lifetime reconstruction. The two main modules are channel correlation extraction block and special channel multi-head self-attention block. In channel correlation extraction block, through the nonlinear process of recombining multiple measurements, we introduce more inter-channel information and promote sufficient feature fusion by using efficient channel attention. In spatial channel multi-head self-attention block, we are considering the global correlation of features in the channel dimension. We enhance the local correlation within the channel by introducing spatial channel attention. Combined with the forward image model, fluorescence lifetime reconstruction network could be optimized in an end-to-end manner. For training our end-to-end framework, we use MSE loss as a fluorescence lifetime fidelity loss to constrain the network optimization. Facial information loss is used as a guidance to optimize the coding scheme to enhance the noise robustness. With this framework, we can optimize high-performance coding scheme, reasonable exposure time allocation, and high accuracy reconstruction network. To demonstrate the overall performance superiority, we compared our method with existing flame methods on real datasets and synthetic datasets. The qualitative results are shown as follows. Our method enabled to reconstruct the fluorescence lifetime of the lowest mean absolute error across different noise levels. Especially under the condition of large noise, the improvement is more obvious. Furthermore, we compared our optimized coding scheme with others when using the same reconstruction network for reconstruction. Our optimized coding scheme is more accurate for the recovery of long fluorescence lifetime regions. At the same time, through testing under different noise conditions, our coding scheme had better noise robustness. To verify the effectiveness of our proposed exposure time allocation, the network module, as well as the facial information loss, we conducted ablation experiments separately. According to various verification results, all the modules we used are reasonable and useful. Lastly, we built a hardware prototype which can use optimized coding scheme and the exposure time to collect actual measurements and then send to the optimized network for fluorescence lifetime reconstruction. We also designed some experiments to verify the feasibility of the hardware system. First, we made a solution of a signal fluorescence lifetime by mixing ethanol and coumarin-6. We use different methods to measure. As can be seen from the statistical results in the upper right column, the measurement results of our method are more accurate and stable. Then we made a scene composed of fluorescent tabs with 2 different fluorescence lifetimes to test our method's ability to recognize symbol patterns. From the results, our method is also clear for edge imaging with different fluorescence lifetimes. Here is a brief conclusion of our method. We propose an end-to-end film framework by jointly optimize differential forward model and the reconstruction network. We achieve high performance fluorescence lifetime imaging, and we build a prototype system to prove the feasibility of our method. For the future work, we plan to improve the current method and the prototype system to adapt to more complex signals, as well as biological experiments. So if you have any further questions or inquiries, please feel free to get in touch with us. Thank you for the listening.
Hi, thank you for the talk. You're optimizing the exposure, right?
Yeah.
So what are the optimal exposures? And for example, the previous talk, there was like an optimal exposure and there was a guideline. There was an optimal delay, which was related to the lifetime of the energy level. So in your case, what were the optimal exposure times and how are they related to the lifetime of the fluorescent energy level?
Why we use exposure time allocation is that for fluorescence material, a prolonged exposure time may cause light damage. So we want to get higher performance in a limited exposure time. So we use exposure time allocation.
I don't understand. Did you look at the time allocation? Is it uniform? Is it non-uniform? The time allocation?
Yeah, it's non-uniform.
And what is the guideline? If you have, I don't know, if you have any intuition on that.
Guidance is our facial information loss.
Yeah. Okay, maybe I'll ask you later about this.
Okay.
Okay, any questions so far? Okay, thank you for the speakers. Thank you for all the speakers here.
See if the sound works.
Hi.
Oh, now we need to set up the sound system. Okay.
I'm Diego.
Okay, perfect. Much better than yesterday.
All right, hello everyone. I'm Christina Matakova. I'm one of the poster chairs. Next, we have our remaining spotlights for the posters. As a reminder, you'll have a chance to vote on the best poster and best demo awards tomorrow. So make sure to stop by all the posters and demos. And here are the spotlights.
Hi, I'm Diego Arroyo, and together with Miguel and Jorge, we present Transient. Transient is a physically based light transport tool for time-gated and time-resolved devices. Its core is based on Mitsuba 3 for leveraging state-of-the-art performance and a Python interface for easy usage and tinkering. We created this tool to be a foundation for novel transient techniques, especially non-line-of-sight imaging. It can simulate light at ultra-high temporal resolutions. Here, we simulate how a light pulse propagates over a turbid medium, as in the femtophotography work by Belten et al. The light pulse comes from the left and travels through the bottom. Our system is designed to help the development of transient imaging methods without the need for expensive hardware and with a modular interface that can be easily extended for your needs. Please check out our links and reach out to us in the poster session. Thank you.
We propose space-time Fourier tachography, STFP, an imaging technique enhancing the exploration of microscopic object movements. STFP aligns spatial and temporal information, enabling dynamic microscopic scene reconstruction. We use a multiplex illumination scheme and embed deep learning parameters with optical flow-based warping constraints. We evaluate our method on simulation cases of dynamic objects and real-world samples and motion. In live Rodifer samples, we achieve sharp amplitude details and saturated phase. Digital refocusing can be applied here to a correct focus plane across different areas. Thanks for your listening.
We propose a novel snapshot continuous wave time of flight that can capture amplitude and depth using a single image. The main idea is to spatially vary the imaging parameter theta linearly along rows or columns during the exposure. The idea of snapshot CW-TOF can be easily understood in the Fourier domain. We can show that the Fourier transform of the snapshot measurement embeds the Fourier transform of the TOF hologram and its twin separately. We can recover the TOF hologram by simply filtering the twin and frequency shifting the hologram. We use the Melexis EVK75027 evaluation kit as the camera and illumination, Thorlab's 2-axis galvanic mirrors for view steering, and a DAC for synchronization. To summarize, we proposed a snapshot CW-TOF LiDAR that is 4 times faster than the conventional CW-TOF and rigorously evaluated the system under various conditions. Thank you.
In our poster, we discuss how to time the initial noise in stable diffusion to generate images in the style that we want. Prior fine-tuning methods often do not match the style correctly. We observe that images generated from the same initial noise often have a more coherent style with each other. So we want to start the generation process from a style-specific noise. This works quite well, but requires to fine-tune stable diffusion with style-specific noise. How is it that the initial noise affects the style, and would it be possible to leverage the initial noise without fine-tuning? Yes, it's possible. During training of stable diffusion, images were never completely noised, and the model learned to copy the low frequency content of the noisy image in the predicted clean image. We thus propose to include desired color or low frequency content into the initial noise in the same amount that the model saw during training. We can then bias image generation toward desired style without any fine-tuning. Thank you.
Hi everyone, my name is Cassandra Yi and I'll be talking about our work on learned, uncertainty-driven, adaptive acquisition for photon-efficient scanning microscopy. Scanning microscopy systems construct highly detailed images of biological specimens by sampling one point at a time. And advances in deep learning have allowed noisy measurements to be denoised so that there is high image quality while reducing the amount of light dosage to a sample. However, deep learning models have been shown to hallucinate, so how do we know our predictions are trustworthy? Wouldn't it be nice if our model could also predict the upper and lower bounds of where the true pixel lies? In our work, we capitalize on these bounds to produce an uncertainty map of the denoise prediction, which essentially heat maps regions of the sample in which our model is most uncertain. Using our method, we show that adaptive acquisition of images, where we only rescan regions of high uncertainty, is still capable of reducing model hallucination while allowing for a 16.7 times savings in light dose. If you're interested in learning more about our work, please stop by my poster during ICCP.
Continuous cost aggregation for dual pixel disparity extraction. In dual pixel cameras, each pixel is divided into 2 pixels sitting under each lenslet. These pair of pixels can be used to create a pair of left-right images, where in-focus pixels are similar in both images. However, out-of-focus pixels generate different point spread functions for each image. Although the 2 images resemble a stereo pair, traditional algorithms such as semi-global matching fail on these images. First, their point spread functions are not similar, and second, the disparities in these images are very small. In our work, which is inspired by SGM, we adapt the algorithm to better fit dual pixel images. We show the performance of our algorithm on multiple datasets, such as DSLR captured images, phone captured images. Finally, we showed that our algorithm can be adapted to standard stereo settings, resulting with similar results to standard algorithms.
We introduce EV de blur NERF, a new method that exploits event-based cameras to recover sharp radiance fields from motion-blurred frames. Our method exploits a learnable event camera response function, as well as model-based priors to effectively merge blurred images and events into a unified, sharp radiance field. We show that thanks to events, our method is capable of restoring fine and sharp details even if they are completely lost in the input motion-blurred training images. On synthetic scenes, our method achieves approximately 3 decibels higher PSNR than image-only methods and 4 decibels higher than event-based methods. We see a similar trend on real-world scenes. In this data, all pixels exhibit consistent motion blur across the whole video, causing image-only methods to perform poorly. While event-based methods perform better, our method still outperforms them, showing an average of 2.5 decibels higher PSNR. Please visit our GitHub page to access code and data.
In this work, we investigate how we can use depth priors to improve the efficiency of single-photon LiDARs. These SPAD LiDAR sensors capture the direct time of flight for light to travel to and return from an object, and are sensitive enough to capture individual photons. To account for ambient light and handle photon variability, these sensors create histograms by counting the incoming photons into discrete time bins. As SPAD sensor technology advances to megapixel resolutions, memory and bandwidth issues arise due to the inefficiencies in this histogram formation. Our idea is to limit the number of bins stored in memory by using a depth prior to guide a foveated region in the histogram. In this example, we use a monocular depth estimate as the prior and simulate a SPAD camera. On the left, depth foveation shows limited bins constrained to the fovea window, increasing depth resolution. On the right, memory foveation uses the fovea window as a traditional gate, maintaining temporal resolution. Our methods produce high quality and accurate depth maps using a fraction of the memory. Thank you for watching. Visit our poster for more in-depth exploration and more histogram foveation methods.
Hello everyone. You may have the experience of taking panoramic photos with your smartphone. Many of you may have wished that you could take panoramic photos in a single shot without needing to rotate your phone. You might have also wished to take panoramic videos. This poster presentation will show you how to make that possible. Our approach is to double the horizontal field of view of a regular camera by combining the horizontal field of view of 2 of them pointing in 2 directions. We use folded prism optics to achieve parallax-free image stitch. We then seamlessly merged 2 images via high-speed imaging processing on mobile ISP hardware to form a panoramic image. Please come to the post to see the TPC demonstration in live. Thank you.
This is the presentation of our work in microscopy. The microscopy has a trade-off between speed and resolution. It's because the optical throughput is limited. The traditional imaging is either low resolution or low speed, which is not good for biological studies. To solve this problem, we propose a deep learning-based virtual scanning method. It's a robust, generalized network with physical priors. For example, the cells migrating very fast in the mouse liver. We can remove the motion artifacts. The method is also published in Nature Methods. Another case is voltage imaging, which need a very high speed to record. With virtual scanning, we realize an ultra-fast 3D imaging at 500 volumes per second. It's a brief summary of our work. Thanks for your listening.
Okay, that's all of them. Do we have any other announcements? Okay.
So just a few small announcements before the coffee break. Should be good. Oh, here we go. Okay. So, first thing first, so our wonderful photo that we've taken is on the home website. So you can download it. It's relatively high res, so you can download it. And if you want even a high resolution, I think Federico will certainly be able to provide this. So the other thing is we posted some information about the reception tonight. So actually, I'm just going to flip through them, but it's again the schedule, right? Can be there by 6. We would have an hour to see the museum. More than an hour, actually. You know, the drinks are on the terrace that is there at 7, but you still have some time to walk through the museum. And then on the top floor of the museum at 8, dinner starts. Now, we recommend you actually take the metro. You know, first M1 to Flon, and then M2 to Ouchy, and walk for the, 7 minutes until you get to the museum. So I'm not going to go in detail through those. These are just the directions to actually go there, get there, and... Or maybe here at the bottom, go left, and then you will run into the museum.